Colloquium speaker gets a gift.
Thank you very much.
I was supposed to, because it's hard to do Colloquium, we thank you for doing Colloquium. That's what I was supposed to say. Yeah. So our speaker today is Nigel Hitchen from Oxford University. He is Savilian Professor Emeritus of Geometry, and he's been awarded many prizes and things of that sort for his work, including the Shaw Prize quite recently in 2016. And today he'll tell us, when the lights go off, he'll tell us about semiflat, hyperkähler manifolds, and their submanifolds.
Thank you.
Thanks.
Okay, so first of all, I'd like to thank both organizers, the Colloquium organizers and the workshop organizers, for inviting me to give this talk, and especially for Martin, because Martin's work has been very influential in my own, and it's really nice to join in with the rest of the people here and wishing him a happy belated birthday. So my contacts with Martin, they go back to, so this is there are mathematicians in the audience who may not have seen this, but workshop participants, this is the fourth time they've seen this. So this is Martin here, and it relates to a meeting in 1980 in Cambridge on supersymmetry. And we were both there, as you can see, with some distinguished people around us. But I have to make a confession, and that is that actually I didn't go to many of the supersymmetry lectures there. There are two reasons for that. One is that I was there in Cambridge with my wife, my 2-year-old daughter, her 2 or 3-year-old friend, and my mother-in-law, and that kind of put some constraints on things. And the second was that I wasn't so interested in supersymmetry at the time. So what really led me to Cambridge was this sort of thing here. So this is a paper by Gary Gibbons and Stephen Hawking, which appeared soon before 1980. And this was all about Euclidean gravity in 4 dimensions, about solutions to the vacuum Einstein equations in 4 dimensions. So I spent quite a lot of the time in Cambridge then talking to Gary Gibbons and not going to supersymmetry lectures. So my apologies to those lecturers, some of them who are here. So what really attracted me to this paper was what's called the Gibbons-Hawking ansatz. So this is a metric in 4 dimensions which satisfies Einstein's equation. So it's a non-flat metric. The Ricci tensor is identically 0. And how do you get it? Well, you just take a harmonic function on R3. So V here is... okay, wrong one. Okay. V here satisfies this equation. So if you like, the gradient of V is the curl of A. And so V is a harmonic function. So, in fact, in my earlier years, I was trying to find explicit examples, complete examples of Einstein metrics without any success. And here, suddenly, was an ansatz where all you did was take a harmonic function and plug it into the ansatz, and you got a solution to this nonlinear differential equation. And not only that, but if you took the function v to be standard sum of one over R potentials, then you got something which was smooth and complete and satisfied lots of very interesting properties. So it was kind of moving on from that led me to Cambridge to talk to Gary Gibbons and others. But so what is this? So this is really the first example of the things that I want to talk about today, or not quite the same kind of example, but the ansatz is important. So let me say this. So this is a hyperkähler 4 manifold. So what is a hyperkähler manifold? It's a Riemannian manifold with a metric G, and it has complex structures I, J, and K, which behave like the quaternions. So Hamilton scratched this formula on the bridge in Dublin all those years ago. So the quaternions gives you three different complex structures which behave in this way, and they are each constant with respect to the metric. So in other words, there's a kähler metric with a complex structure for each one of these, and the most important thing to say is that there are three kähler forms, omega 1, omega 2, and omega 3. Now, a few years after 1980, so this was 1983-84, I spent 2 semesters here in Stony Brook. And just before then, in the summer of 83, Blaine Lawson was visiting the UK, traveling around giving lectures. And he passed through Oxford and he said, well, the one person you should talk to in Stony Brook is Martin, because he has this construction of hyperkähler metrics. All you do is you take a representation of a group, you turn a handle, and out comes the hyperkähler metric. So that was a very intriguing comment. And so, in fact, I'd arranged to come here long before I heard about this. So once I got here, I sought out Martin, and indeed we worked together. Now, working with Martin, as many of his co-workers know, is it's a two-edged sword. One of the first things I learned about Martin was that he never eats lunch. So, we'd be working away, and I'd be kind of looking at my watch and getting nervous, and he would keep on going and going and going. But I've heard since, of course, he's an excellent cook, and obviously, he waits till the evening before he appreciates these things. Anyway, so by the time I'd 83, 84 was over, well, it took some time, as you can see, 1987 to write the paper. But as you can see, I appreciated supersymmetry far more than I did when I was in Cambridge a few years before. So this was a paper, so I should say that Ulf Lindström was here as well, on and off, and so this is a joint paper with Anders Karlhede and Ulf and Martin. And this has been very influential, at least certainly in my own work. And so let me say something about this. So one of the things that it really introduced was the notion of a hyperkähler moment map. So this is an extension of a piece of symplectic geometry. So if I have just think of one symplectic structure. So if we have a symplectic manifold M with a symplectic form omega, and suppose we have a Lie group G acting on this, then every element of the Lie algebra of G gives us a vector field. That vector field preserves the symplectic form, and if you're in a good situation, then it's the derivative, if I contract it with the vector field, it's the derivative of a function, the Hamiltonian function. And you put all these functions together and gives you a map, called the moment map, to the dual of the Lie algebra. So you evaluate this moment map on an element in the Lie algebra, and you get the function fa. Now, actually, for a moment map, what you require is that this should be equivariant, meaning that the natural action of the group G on the dual of its Lie algebra, the moment map mu should commute with that. The action on M and the action on G dual should commute. So that's sorry. That is assumption that is, if you like, part of the definition of a moment map. So a moment map may not always exist because, on the first place, a Hamiltonian function may not exist, and secondly, you may not be able to make it equivariant. But we'll come to that a little bit later. So if you now have a hyperkähler manifold, then it's got these three symplectic forms, the three kähler forms for the complex structures I, J, and K. And so you get a moment map for each one of these, hopefully, which is a function for each one of these and for each of the 1, 2, and 3. So the hyperkähler moment map is now a map to 3 copies of the dual of the Lie algebra. So it's a tensor product of R3, which you can think of, as you like, as the imaginary quaternions times G dual. And it explains, if you like, the Gibbons-Hawking ansatz, because in that case there's a circle action, a tri-holomorphic circle action, and the coordinates on the R3 are actually the three hyperkähler moment maps corresponding to that action. So the structure of that ansatz is just comes from this moment map construction, and then it's not hard to check that the coefficient has to satisfy that linear equation. So here's the abstract of the paper, and one of the things which comes up there is this Legendre transform construction. So what is this? This is really a generalization of that ansatz, that Gibbons-Hawking ansatz. So now, instead of 4 dimensions, you have a hyperkähler manifold of 4k dimensions. The dimension always has to be a multiple of 4, just because the tangent space is a quaternionic vector space. And now you have a tri-holomorphic action of, let's say Rk, the abelian group Rk, or it could be the product of circles. And then, hopefully, you get a moment map, which takes values in this 3k dimensional space, and then the orbits of the Rk action fill out the fiber this. So this is a direct generalization, but you need now a function to replace that harmonic function, and the function has to satisfy the condition that it should be harmonic on each 3-dimensional subspace given by this form. So you take a vector in Rk, you look at A tensor R3, that's a 3-dimensional subspace of Rk tensor R3. You want a differential equation which tells you that f actually should be harmonic on each of those. And okay, so I've written down part of this equation. There's another one which involves the cross terms. In fact, this equation and the other ones appeared in the first lecture this morning in a somewhat different context. So, this equation, so you need the cross terms as well, vanishing, the x's and the z's. And of course, there's a special case, if you look at this and the others, where f is independent of x, and then this tells you that f is a holomorphic function. So this is kind of a trivial solution to this, but it's what I'm going to talk about. So the general solution to these equations was what Martin and Ulf, I guess, they figured out even before we met, in terms of a contour integral. My contribution to the paper, as far as that was concerned, was showing that it was basically in twistor space. You can interpret that as a sheaf cohomology group, an element in a sheaf cohomology group, and it fitted in with many things in Penrose's twistor theory. But for this talk, all I want to do is to look at the case where this function f is independent of some of those variables. So you might say it's boring, but actually I hope it's not so boring. Actually, if you go back to the 4-dimensional situation, then hyperkähler in 4 dimensions is the same as Calabi-Yau. So what we know is that if you want to find a Calabi-Yau metric, then you need to solve a complex Monge-Ampère equation. But then if you impose this R2 invariance that comes from insisting that function f should be independent of x, then that comes down to the real Monge-Ampère equation. So what you get here is that this famous nonlinear differential equation can be solved by a harmonic function. So, that's quite a cool thing if you think about it. But then, 200 years ago, Monge thought it was pretty cool as well. So this is a very old result, but you can read it as a consequence of the Gibbons-Hawking ansatz, or you can say it's an old result. But at least it shows that some nonlinear differential equations can sometimes be solved by reduced to linear equations. So let me give you now a better definition of what I mean by a semi-flat hyperkähler metric. So now I want it to be, I want to have a torus action. I want to wrap up the RK into the action of a product of circles. So I want to have a tri-holomorphic action by 2K now. So M is a 4K dimensional hyperkähler manifold. And instead of having an action by a K-dimensional group, I've got now a 2K dimensional group, which is tri-holomorphic. And I want the orbits, so the orbits are now even dimensional. I want them to be complex with respect to the complex structure I. So we've got I, J, and K, and then I want to insist that they're complex. So these are complex tori, complex Kähler tori inside this 4K dimensional manifold.
So is there a complex structure so that the action is complex with respect to I?
Well, the action is a translation action, yeah. So it's just translation, so it's that preserves complex structure. Yeah. And this is locally defined by a function, by a real, by taking the f, if you like, to be the real part of a holomorphic function of k variables. So at this point, and this is kind of coming back to Dennis's point. So there's a paragraph here that I took from our paper, which I've always felt a little bit guilty about, actually. It's not that it's wrong. I think it's right. So it says that there are various things, but in any case, if G is a compact group, you can assume that it's equivariant. So it is true that for a symplectic manifold, for a single symplectic manifold, then you can you can adjust things so that a compact group will have an equivariant moment map, so long as there are Hamiltonian functions. But there's a kind of implication, I think, in our paper that this is going to work for all forms, omega 1, omega 2, omega 3. I don't know whether we realized that at the time, but we weren't. So actually these semi-flat ones, it's a situation where actually you can't have an equivariant moment map, because you see once the orbit of the action is complex, then the Kähler form omega 1 is going to be non-trivial when we restrict to those orbits. So that means that if we take some of the vector fields, say, I've called them Y here, Yi, Yj, these killing vector fields, then applying omega 1 to a pair of these will give us something non-zero, but these are Hamiltonian vector fields, so it's the same as applying Yi to the Hamiltonian function. But if it's equivariant, then this is an abelian group. It should act trivially on its Lie algebra, and so that should be zero. So this is not exactly a mea culpa, because there's nothing wrong in that, but there's at least in my mind, there was a kind of implication that we'd settled that and then we went through. So this is a situation where there isn't an equivariant hyperkähler moment map. If you restrict to a k-dimensional linear subspace for which is isotropic for omega 1, then you're all right. So the k-dimensional part is fine. Anyway, that's something to bear in mind. So what I've said was that I want to, this is what I want to study, and the question is why. So there are three reasons. One is to do with the moduli space of Higgs bundles, something which has occupied me for a long time. Another is the notion of special Kähler manifolds. And thirdly, I want to check some of the predictions of mirror symmetry by restricting to semi-flat hyperkähler manifolds. And that's the question of when distinguished submanifolds come into play. So let me tell you why these things are relevant. These semi-flat hyperkähler metrics are relevant to these three areas. So what about Higgs bundles? Well, this is a subject which actually goes back to when I was here in Stony Brook in 83, 84. And it comes from the second point that we have here in the abstract, the symplectic quotient. So a generalization of the symplectic quotient, where you replace a symplectic manifold by a hyperkähler manifold. So if I have a hyperkähler manifold, then I'm just repeating myself here. I've got, suppose I have a moment map, I have a hyperkähler moment map like this. Then if I look at the inverse image of 0 under this moment map, then divide out by the action of the group, then I get a hyperkähler manifold. If this is a manifold, if the group acts freely on the inverse image of 0, then this is hyperkähler. And this is the construction that Martin was doing, that Blaine told me about, in the case where you actually have a vector space. So you start with your manifold M being a quaternionic vector space. So you have a representation of the group on this. And then you turn the handle, which means looking at the moment map, look at the inverse image, take the quotient. And lo and behold, you start with a flat space, and what you get out of it in many situations is something which is definitely non-flat, which has metric, which satisfies Einstein's equations and everything. And so Martin and his collaborators have produced hyperkähler quotient constructions of several of the standard metrics, including the ones that were in the Gibbons-Hawking paper. So that was a very powerful construction. But at the time, the use of symplectic geometry and moment maps, it was very much in the air, especially in Oxford, because with Michael Attier and Raoul, had worked with Raoul Bott on looking at a moment map interpretation of the Narrow-Simons-Seshadri theorem, and Francis Kirwan was working on moment maps and algebraic geometry, GIT quotients. So everything was in the air, and so kind of reformulating what Martin was doing in terms of this hyperkähler quotient was a relatively easy issue. Writing a paper which matched this and my view of hyperkähler manifolds via twistor theory with the supersymmetric one was another question. But anyway, it was a very instructive exercise. So when I learned about this quotient construction, then I probably sent some message to Michael Attier in Oxford, and he said, well, we must use this in an infinite dimensional context to get structures on certain moduli spaces. And the first one we looked at was the moduli space of monopoles, of solutions to the Bogomolny equations, because I think Taubes had observed that the tangent space, the moduli space, had a quaternionic structure, but the quotient construction told us immediately, in this infinite dimensional context, that what you had was actually a hyperkähler metric. And in fact, that summer in '84, Attier and I worked hard to actually find that metric in the lowest dimensional case. So then I started looking for other types of infinite dimensional hyperkähler quotients, and then there was this one. So you start with a compact Riemann surface, and you take a principal G bundle on it. G is a compact group. You look at the space of the infinite dimensional affine space of connections on this principal bundle. So that's an affine space. So the difference of two connections is a one form with values in the Lie algebra. But but actually, if you take the product, well, I haven't put the complex structure on this because there's a metric as well. But essentially, if you look at the pair of objects, or the cotangent bundle, if you like, of this space of connections, then this is an infinite dimensional flat hyperkähler manifold. There's a group acting on it, which is the group of gauge transformations. And when you write down the three components of the hyperkähler moment map, what you get in local coordinates is something like this. So you have a connection A, and phi1 and phi2 are the two components of this one form with values in the Lie algebra. So phi1 and phi2 are locally here are Lie algebra valued functions. So when you set these equal to 0, then the last two equations give you a Cauchy-Riemann equation, and the first one is a nonlinear gauge theoretic equation. So these are called the Higgs bundle equations. So the inverse image of 0 under this moment map, modulo the group of gauge transformations, that is the moduli space of solutions to those equations, which has a holomorphic description in terms of pairs of objects like this, a holomorphic principal GC bundle, and a Higgs field, which is a holomorphic section of this Lie algebra bundle tensored with a canonical bundle. And then there's a metric or a reduction to the maximal compact, which satisfies this nonlinear equation here. So you can either think of it as a holomorphic object in terms of equivalences of pairs of objects, holomorphic vector bundle and so-called Higgs field, or equivalences of solutions to these equations, modulo gauge equivalence. Anyway, this as a consequence of the hyperkähler quotient construction, it has a hyperkähler metric, but we can't work it out. It's far too complicated. You can't solve these equations explicitly. But what happens is that there is, in fact, a semi-flat approximation. So there's been quite a lot of recent work about this and about the degree to which it is an approximation. And this paper is one of the one which contains perhaps the most information. But there's been work by a lot of people. Actually also by physicists, Andy Knightsky is a mathematician, physicist. Anyway, it's quite a recent growth point, determining to what extent, as you go out to infinity in this non-compact moduli space, the actual hyperkähler metric is approximated by a semi-flat version. So that's my first reason for wanting to study these particular hyperkähler metrics. The next one is a piece of geometry which is probably familiar to the physicists here. So in fact, it originated in works of two of the participants in this workshop. Jim Gates and DeWitt here, independently. In mathematical terms, it was described very nicely by Dan Freed in this paper. So these are called special Kähler manifolds. So the thing to note about this is that if you're familiar with Kähler geometry on compact, complex manifolds, algebraic varieties, this is not the right flavor. So this is there are no compact manifolds which have these special Kähler metrics. It's a different type of Kähler structure. So what does it consist of? It consists of a space, a manifold, which has a flat, torsion-free affine connection on it. So that's not I know this is a Kähler manifold, so that's not the Levi-Civita connection. That's a different thing. It's an affine connection. But it does preserve a symplectic form. So we have a covariant constant symplectic form here. And we have a complex structure such that when you couple it with the Kähler form, with the symplectic form, it does give a Kähler metric. But the complex structure is not covariant constant with respect to the flat connection, but it satisfies another equation here, which you can say is that if you like, if I take the covariant derivative of a vector field, then that is what I have. I mean, I could write it as the flat exterior derivative of I as a one form with values in the flat tangent bundle. That should equal 0. But locally, it means that it's the covariant derivative of a vector field. So this is slightly unusual to a differential geometer, slightly unusual structure. But it occurs in lots of different areas. So in particular, if you look at the base of an algebraic completely integrable system, so if you have a complex symplectic manifold, which is algebraic, and it has a Lagrangian fibration by abelian varieties, then the base space of that, the base of the fibration, has on it one of these special Kähler metrics. That's actually a special case of a more general situation where if you look at the moduli space of compact, complex Lagrangian submanifolds inside a Kähler manifold, that also has one of these special Kähler metrics on it. And it is a subject which actually has appeared in the literature of affine differential geometry. You can call these things parabolic affine hyperspheres if you want. So let me just explain why this structure occurs in this first situation. So first of all, if you think of a real symplectic manifold, which is an integrable system in the sense that it's fibered by tori, by Lagrangian tori, then what can you do? Well, if you take a tangent vector on the base, what does that do? That's an infinitesimal variation of the fiber. So it's a section of the normal bundle of a fiber. Now, if I lift that, so it's only a section of the normal bundle, if I find a vector field which restricts to this, contract it with the two-form omega and then restrict to the fiber, then that's independent of the way in which I extend this, because omega vanishes along the tangent bundle of the fiber because the fiber is Lagrangian. So this is a well-defined one-form. Oh gosh, what's happening here? Anyway, it's a well-defined one-form there on the fiber, and it's actually closed. So it has a cohomology class. The fiber is a torus. And so this way we have an identification of the tangent space at a point on the base with the cohomology, the first cohomology of the fiber over that point. Now, if I have a contractible neighborhood in the base, then there's a canonical isomorphism between the cohomology of any two fibers. All you have to do is look at the restriction from the cohomology of the inverse image of that contractible neighborhood to any one of the fibers. That's an isomorphism by homotopy invariance. And so that gives you a flat connection on the tangent bundle of the base. So that's the flat connection. So now if omega is exact, if it's D of a one form, then because the fibers are Lagrangian, that one form, the one form is closed on the fiber, and then you can define functions, locally defined functions. You can integrate alpha, this over generators of the homology. That gives you flat coordinates in this structure. So not only is this vector bundle, the tangent bundle, not only is it flat, but it's a torsion-free affine connection because you have flat coordinates here. Now, when it's a complex algebraic Lagrangian fibration, then you've got a Kähler class, which gives you a flat symplectic form, so that we're now identifying tangent vectors with one forms on the fiber, and so integrating against the power of that two form gives you a skew form which just depends on the cohomology class, so it's covariant constant with respect to this flat connection. So then when you put the complex structure in, so the base is complex in this situation, that's when it satisfies this other differential equation. So actually, so now if we have a semi-flat hyperkähler metric, then that is, apart from the integrality of the cohomology class, that is an integrable system. We have this family of complex tori, and they are in fact Lagrangian. You find that the omega 2 and omega 3 are actually vanish. So omega 2 plus I omega 3 is the holomorphic symplectic form. It vanishes along the fibers, and so we could use omega 2, say, the real symplectic form omega 2, to define flat coordinates on the base. And that is, in fact, so those coordinates are effectively the moment map for this action of TK. So that's so even in the, so we could say we start with an algebraic integrable system. We have this, the holomorphic structure of that gives us this special Kähler structure on the base, but we would also see it in a semi-flat situation. But then, more importantly, there's a reverse, that if I have a special Kähler structure on a manifold, then it defines a semi-flat hyperkähler structure upstairs. So we can go backwards and forwards. There's a formula here which gives, there are many, many different ways of writing this, but there's a formula here which tells you in terms of a function phi, which is the Hamiltonian function for the vector field x, which generates the complex structure. These are the complex, the symplectic forms. So given any special Kähler manifold, we can construct on a bundle over it, we can construct a special semi-flat hyperkähler metric which locally looks like the cotangent bundle over it. So that we can go backwards and forwards. And so in the case of the Higgs bundle moduli space, there is in fact a natural algebraically completely integral system that gives you a special Kähler structure on the base, and the corresponding semi-flat Kähler metric, hyperkähler metric, is the one which is the asymptotic approximation. Okay, these are the formulas which relate that function phi to the function f, but that's not particularly important. So one thing is that so there's one extra special case of this, which is where this vector field x, which automatically satisfies these two conditions here, if that satisfies this third condition here, then it means it generates a circle action which fixes one complex structure and rotates the other two, or better said, it rotates the symplectic forms, leaves one of them fixed and rotates the others. Then the special Kähler manifold is then called a projective special Kähler manifold. It's not. I mean, there's some dispute about what the right notation should be. As an algebraic geometer or whatever, you would think of the quotient by the C star action as being the special one, but I think this is the one which is kept. So it's got we think of this special Kähler manifold as having a C star action, and therefore somehow there should be a quotient which is projective. Anyway, that's just nomenclature. Okay, so yeah.
That's Fried's terminology, not the physics terminology.
Yeah, as I understand it, yes, okay.
Maybe simple question. You just skipped one slide with the example that was similar to free potential. I know something about this, but
yeah.
Yes. Some another case, yeah.
So this holomorphic function is like the prepotential for the special Kähler, yeah.
So exactly the simplex Z and simplex form is like no, it's not that, but there is a second derivative for the prepotential. Is it Kähler or special Kähler?
I mean, there are many different ways of looking at this, and there's a cubic form. There's the third derivative of the potential. That relates to what's called the Donaghy-Markman cubic. I just wanted to restrict to things which came directly from if you like, the Legendre transform construction. So what about mirror symmetry? So this is mirror symmetry not for Calabi-Yau threefolds, but for hyperkähler manifolds with a fibration. So this is the SYZ notion of mirror symmetry. So as applied to, as it was originally formulated in terms of special Lagrangian fibrations of a Calabi-Yau, but it works it works in this hyperkähler situation. Well, it works. I mean, the procedure can be defined in this hyperkähler situation because a semi-flat hyperkähler manifold has a complex algebraic Lagrangian fibration. This is so relative to a hyperkähler metric, this is a special Lagrangian fibration. And the SYZ mirror says that you should replace the abelian variety fiber over a point X by its dual, which is the moduli space of degree 0 line bundles on A. So you dualize the fiber. And in this setting, we can think of that purely in these holomorphic terms, these I-holomorphic terms. So these are this is a good testing ground, if you like, for seeing whether SYZ mirror symmetry actually works. And in particular, in the case of the Higgs bundle moduli space, it's supposed the SYZ mirror procedure is supposed to correspond to Langland's duality of the corresponding groups, and so checking this at the level of the semi-flat approximation is something which is a reasonable thing to do. So just one point about this duality. So an abelian variety is actually not that different from its dual because, and in this particular case, so in this semi-flat situation, the Kähler form omega 1 actually is invariant under the under the action, the T2k action. So it's basically a constant in terms of the flat coordinates on the torus. It's actually a constant form, and if it's algebraic, then basically it corresponds to there is a line bundle whose first Chern class is given by this form, and then you can map an abelian variety to its dual by this natural process. So you take this line bundle whose first Chern class is theta, you translate it you take an element A in the abelian variety, you translate it and then tensor with its inverse. That is a degree 0 line bundle on the abelian variety. So there's a map there from the variety to its dual. This has a finite kernel. So there's some sense in which the dual abelian variety is very similar to A, and for example, for the Jacobian of a curve, this is actually an isomorphism. So that's just something to bear in mind when we come to the relationship between A and the dual. Okay, so my talk is really about submanifolds of these special Kähler manifolds. These semiflat. Thank you. Hyperkähler manifolds. And there are two particular types of submanifolds. So there are complex Lagrangian submanifolds, complex with respect to I, and there are hyperkähler submanifolds. These are rather different. So to have a hyperkähler submanifold of a hyperkähler manifold, it's not like having a Kähler manifold of a Kähler manifold. There are lots and lots of those. If I have any complex submanifold of a Kähler manifold, that is automatically Kähler. But that doesn't apply, well, it would apply in the hyperkähler situation if the tangent space was preserved by I, j, and k, but that's a very strong condition. It means that the submanifold is totally geodesic. It's a locally determined. If you give me a hyperkähler metric, I can expand around there and tell you whether there are any hyperkähler submanifolds around that point. It's very local. Whereas complex Lagrangian submanifolds are much freer. So why do I want to think about these and the relationship between them? Because these are the supports of. So this is the support of a BAA brane. So this is something, a complex Lagrangian submanifold is something which is complex with respect to complex structure I, and is Lagrangian with respect to complex structures or the symplectic forms omega 2 and omega 3. So it's a brane, it's a complex thing as far as the B model is concerned, and it's a Lagrangian object as far as the A model is concerned. And the support of a BBB brane is supposed to be a hyperkähler submanifold, which is something which is, so that's holomorphic with respect to all the complex structures I, j, and k. And, well, the point is that somehow these should be interchanged in some respect by mirror symmetry. There is, in fact, some extra data, which will become apparent later on, which involves a bundle over each of these, but I don't want to mention that at the moment. So, okay, so this is a mathematics colloquium. So I'm going to give you a little theorem, which gives us some information. So let's suppose that I have an algebraically completely integrable system. So this is a fibration by abelian varieties. And suppose I have a C star action on it, which comes from a C star action on the special Kähler structure on the base. Okay, so then an invariant. So I'm looking for C star invariant complex Lagrangian submanifolds. Then it has the structure. There's an open set which has the structure of a fibration over a special Kähler submanifold. So one which is invariant under C star. And each fiber is the disjoint union of translates of an abelian subvariety. So this is saying it straightens out. You know, we start with some Lagrangian, and if we impose this C star invariance, then actually it kind of straightens out. Though I should mention that actually in most of the examples, And there are lots of examples in this Higgs bundle moduli space. This fiber is finite. So if you like, the abelian subvariety is just a point. And okay, so this is just, so how do you do this? So first of all, so we look at this holomorphic symplectic form, okay, which is basically built up out of the omega 2 and omega 3, and suppose X is the vector field generating this circle action. Then if L is, so L, I call L the invariant Lagrangian, then if it's invariant, then the vector field X is tangential to the Lagrangian, but omega C vanishes as a 2 form on the Lagrangian, so this 1 form, this contraction of omega C with X vanishes on the Lagrangian submanifold. So now let's restrict this projection in the fibration to the Lagrangian submanifold and look at a generic point where we have where it's a regular, so where the derivative is a maximal rank onto the image. So we have the image, which is P of L, and we have a fiber, which is the intersection of L with A. So I'm just taking one, at the moment I'm just taking one particular fiber, let me just call it A. So what do we have here? We have a non-zero, so on A itself, this holomorphic 1 form is definitely non-zero. In fact, what it is if you look at the infinitesimal variation of A by pushing it along the C star action, that's defined by a 1 form, just as I described in the real setting, and this is the 1 form. So these abelian varieties are not invariant, none of them are invariant under this action. So we have a non-zero holomorphic 1 form which vanishes on this submanifold L intersection A. Now, I have to remind you, maybe you know already, about something called the Albanese variety, which is an abelian variety which is constructed out of holomorphic differentials. And so it's a generalization of the Jacobian, if you like, or the Picard variety. But anyway, it has this universal property that if you have a map to some abelian variety, then it factors through the Albanese variety. So there's a map from M to the Albanese, just given by integration of the holomorphic 1 form over a curve. So what do we have here? So now we have a 1 form which vanishes on this intersection, and that means that it vanishes on the image of the Albanese. So any 1 form on the Albanese, so every holomorphic 1 form on L intersection A is restricted from the Albanese. The Albanese maps into this image AL, and so this 1 form, which we know vanishes on this intersection, vanishes on this abelian subvariety, this image of the Albanese. So now, if you look at the homology, the integral homology inside of the subvariety, then what that means is that the periods of this 1 form actually vanish on. So if you like, do this over the rationals, you can choose a basis for H1 in here, which extends to a basis over here. And so that means that these periods actually vanish on some of these basis elements. So that's equivalent to saying that, okay, and now because of this relationship, this most important relationship, which says that the omega 3, which is the imaginary part of this, so omega 3, which is the imaginary part of the symplectic form, is actually d of something, which is the interior product of omega 2 with X. Then this 1 form here vanishes on these periods, which means that actually you have some flat coordinates which are vanishing downstairs. So the flat coordinates in the special Kähler base are given by integrating a primitive for the symplectic form over these cycles. So what does that mean? So if you look at that, that says that on the one hand, upstairs we have the dimension of the Albanese. They call that M, complex dimension M. Then we have at least 2M real constraints on the image given by the vanishing of these coordinates. So the dimension of the image downstairs is less than or equal to the dimension of the base minus M. On the other hand, the intersection lies inside the abelian variety, so we have an inequality like that. But then, because L is Lagrangian, its total dimension is given by the dimension of the base, and so we get an inequality which is an equality, which means that actually each of these inequalities is an equality, so that actually the intersection is the image of the Albanese. So each component is actually isomorphic to a translate of the Albanese variety, or the image of the Albanese variety. So that's an abelian subvariety, and the base is given by the vanishing, locally by the vanishing of these. Okay, so one final thing is that these linear constraints, so that was just, what I was just looking at was just one fiber. These linear constraints have rational coefficients, which means that they're locally constant. And so what we get is, for the nearby fibers, we get a real linear subspace of the base in terms of the flat coordinates, and this is a special Kähler submanifold. Okay, so now in the last 10 minutes, let me address this issue of mirror symmetry. So mirror symmetry is supposed to interchange BAA branes and BBB branes. And a complex Lagrangian, together with a flat line bundle over it, or flat vector bundle over it, is basically what a BAA brane is. So what SYZ mirror symmetry, what does it do? You fix the base and you take the fiber, you dualize the fiber. So if we have an abelian subvariety like we do have, AL of the fiber, then we could define its annihilator, if you like, in the dual abelian variety to be the line bundles on A, which are trivial on this subvariety. So that gives us so if we now take a Lagrangian, I use that theorem to say that it's given by a family of translates of an abelian subvariety. Then by taking the annihilator, what we get is a family of complementary abelian varieties in the dual, in the mirror, I should say. And in fact, if you look at the tangent space to this dual, and you identify tangent spaces by using the map from A to A dual, given by the Hermitian form, then it turns out to be the orthogonal complement. And so what you get is that, in fact, what you get on the mirror is actually a hyperkähler submanifold of this semiflat metric. So we start with a C-star invariant Lagrangian, and we do this annihilator construction, and then in the semiflat situation, we get a hyperkähler submanifold. So this is, in some sense, a kind of procedure which seems to confirm what mirror symmetry should be doing. I should say that actually the argument about the Lagrangian, the C-star invariant Lagrangian, actually works. You don't need the semi-flat situation there. And so in the genuine Higgs bundle moduli space, that result holds, which means that when you do this procedure, what you get is in fact on the mirror, what you get is a complex submanifold, which is complex symplectic and is given by is an integrable system as well. But what you can't assert a priori is that is a hyperkähler submanifold. Only in this semi-flat situation can you assert that. On the other hand, if there is such a hyperkähler submanifold, then this will be the semi-flat approximation. And so, so I should say also that we have a special Kähler submanifold of the base. So in the semi-flat situation, then this is the hyperkähler submanifold associated to the special Kähler one by this construction. So, okay, so finally, what about the symmetry of this? What about going backwards and forwards? Well, obviously, it's quite clear you can't go backwards and forwards because what would be suppose the Lagrangian intersects the fiber A in a finite number of points. Suppose the abelian subvariety is zero-dimensional, then the annihilator is everything, And so there are lots of different Lagrangians, C-star invariant Lagrangians, which give you the whole mirror space as the support or the potential support of the brain. But that's where the other condition comes in. That for as far as a BAA brain is concerned, the flat vector bundle is not a big deal, but a BBB brain has a hyperholomorphic bundle. It's supposed to have a hyperholomorphic bundle over it, whose rank is given by, if you like, the number of components of the intersection of the Lagrangian with the abelian variety. So that's the kind of the resolution of what seems to be an imbalance, that there seem to be lots and lots of Lagrangians on one side, very few hyperkähler submanifolds on the other side. On the other hand, that deficit should be made up by hyperholomorphic bundles. But that's another issue. Okay, so let me end up by saying that I appreciate very much the opportunity to thank Martin for all his his influence on my work. I also thank him for this. So this is one of the few pictures I have of him, which was 12 years ago at my 60th birthday conference in Madrid. So well, there's only one more thing that I could say. Thank you, and once more, very happy birthday, Martin.
Are there any questions? Mark?
These are the same semiflat, same notion of semiflat hyperkähler manifolds that arise with the CMAT.
Yes, yeah.
Historical description.
Yes, sure. Yes, in fact, when you do it so the tutorial description for the Legendre transform was a class in an H1. So when you have these which are given by these holomorphic functions, then actually that H1 appears as via a connecting homomorphism in a long exact sequence from an H0. So you don't have to use it that way, because you can, you just take a holomorphic function and you don't need to do any contour integration, but you could do if you wanted to.
And the T2, if you go upstairs before you start with the special geometry, the T2 has to do with the electric magnetic duality. That this isometry isn't just an S1, but it's an S2 for each. The T2K.
T2K, yes.
With K electromagnetic isometries. The doubling comes from the electric magnetic duality.
That I refer to. Yeah, I would like to confirm that, but yeah.
Other questions?
Let's thank Nigel again.